Okay, so this is the last example of Gauss's law, applying it to finding the electric field around an infinite sheet of uniform charge. So this particular type of symmetry is called planar symmetry. Obviously, a sheet of charge is in a geometrical plane. So what we're going to have here is let's fill in the picture a little bit. We have a plane, and we're going to put some charge on it. And the charge is going to be uniformly spread out. And of course, this plane extends to infinity, kind of in all directions, right? Something like that. So we cannot really talk about like putting plus q on this sheet because it's an infinite sheet. So instead, what we'll talk about is we'll just talk about the density of charge on the sheet. So the charge per unit area. And the units for that, of course, would be coulombs per meter squared. So we're going to put a positive charge density on the sheet, and that's going to characterize the charge. Okay. All right. So let's say that our goal is to derive a function for the electric field, and you know, and we know in this case that the field itself is going to be uniform. So it doesn't really make too much sense here to talk about the electric field as a function of radius, because it's not going to depend on the radius. In fact, at this point, what we might do is even sketch a few electric field lines in, right? And so the electric field is always pointing away from the charged surface. So if you're on this side of the charged surface, the field points to the right. If you go on the other side of the charged surface, the electric field points the other way. And so the field is going to be every place perpendicular to the sheet and always pointing away from it. Okay. So let's write down Gauss's law. And there it is. And so now our mission is, you know, we have to like decide on a shape of a Gaussian surface to use that's going to make sense. And here's the key. The key is we're going to pick a surface that is basically going to have flat end caps. Now, this is a cylinder that I happened to draw, and the fact that it's a cylinder isn't really that important. What's really important is the fact that you've got flat ends on the cylinder. Okay, it's kind of like a parallel piping where you have flat ends. In other words, this could have been kind of maybe a rectangular box too, right? My Gaussian surface could have been rectangular. It doesn't have to be a cylinder. It's not important. What's important is that this face is going to be parallel to the plane. Okay, and then for this part, we could say that any shape will do. All right, so the cylinder part isn't that important, but the face right there is. And so the reason is because the electric field is going to come through, and it's going to poke through, and that electric field is going to make a nice alignment with that surface. So my dA is the surface vector for this entire cap, and dA and electric field are perpendicular there. And so that's going to help us out when we write this. Also, on the back side, you have an area vector which points to the left. And that's because the rule is for Gaussian surfaces is the area vectors always point away from the center of the shape. So back here you've got a dA vector and an electric field vector, which are also doing the same thing. Okay. All right, so what do we want to do here? There's really not much calculus to do, but we could talk about looking at the flux through the walls, meaning the walls of the cylinder. So this is the wall here. And we're also going to have to add the flux through the ends, which are the flat surfaces here. And those are the two things we have to put together to evaluate the left side of Gauss's law. Okay. So, since our shape here is parallel, the wall is parallel to the electric field, then we can conclude that there is no flux through that wall. So that's why the shape doesn't matter here. Any shape will do, because if you made this a rectangle, the rectangle would also have zero flux through the walls, because the rectangle would be, that face would be parallel to the field. So that's nice. Now, how about on the ends? Okay. So for the ends, what we're going to do is, it looks like we actually have two things to consider here. And I hope you can see that both ends are going to have a positive flux. Okay. So I'm going to have a factor of 2 that comes out in front, because I've got to take into account the fact that there are two faces. And then we say, well, what is the flux going through here? And it's going to be E and times the area integral of the end. Okay. And what we're going to do is we're going to just say that this entire thing has an area of A. So that integral would be A here, and that's just the area of an end cap. And the factor of 2 comes along there. So to recap, no pun intended, what you're doing here when you find the flux for the ends is you're multiplying the electric field times the area of the cap, and we're just calling that A here. And then you multiply by 2 because there's two caps. Okay, so we're almost done. So then you look over on the other side here, and you've got Q enclosed over epsilon 0. You should have a feeling by now that this area is kind of arbitrary, and we do not want to have it in our final result. So we have to think about how we could get rid of Q enclosed. And this is the exact same trick we played with the line of charge. So we come back to this over here, and we know that Q enclosed we can write the Q enclosed is equal to sigma. Oops. Funky sigma. Sigma times A. Okay. Q enclosed is equal to sigma times A. Now, where does that come from? Well, remember, go back up to your picture, and that area here that we called A is the same area right here. And there is a certain amount of charge that's enclosed in that area, and you could calculate it by multiplying the density times that area. So the charge that's enclosed within this Gaussian surface is basically the charge that's enclosed in that little circle there. And so that allows us to do the substitution. And I think you can see that nice things happen because the area is really not important. So it cancels out. And our electric field turns out to be that nice result that we derived last week using a completely different method. So the electric field is equal to the surface density divided by 2 times the permittivity constant. And once again, I'll just point out that there is no R dependence here. In other words, E is constant, and you could say it's also uniform. And we know that already, but this kind of Gauss's law shows that, shows that to us. So that is the final result, and that's the one that you should also memorize that result. So a single sheet of charge will have an electric field on both sides with that strength, always pointing away from the sheet if it's positive. And again, if you have two sheets which are oppositely charged, so plus sigma, minus sigma, that gives you a field which is actually twice the strength because you have to use superposition there. So in this case, the electric field would be sigma over epsilon naught. And we talked about that before, but these two fields combined their strengths. Okay, well that is the final example of how to apply Gauss's law to come up with an electric field. So good luck on finishing up your assignment.